The McGill AI Podcast.
Hello, everybody. Welcome to the first episode of the McGill AI Podcast. My name is Kostov. I'm here with Bonnie, and we are tremendously excited to have Professor David Rolnick joining us today. Professor Rolnick is an assistant professor at McGill and Canada's CIFAR AI Chair. He teaches at the School of Computer Science and is a researcher at Mila. Professor Rolnick also recently received the honor of being named a pioneer in the MIT Technology Review's 35 Innovators Under 35 Professor. Thank you for taking the time to speak with us today.
Thank you so much for having me. It's a pleasure to be here.
Yeah, so today we're going to talk about a variety of things, about your research interest, how machine learning can be applied to tackle climate change, your research in deep learning and math. But first, let's start off with a bit about your background. Can you tell us a bit about your personal background and your journey into academia?
Yeah, so I started out being interested in a lot of things, including math, including natural history. I would spend a lot of time looking at insects, especially moths. That was me through high school. I was also really passionate about music, and then I went to college and studied math and music. Music was opera singing, and then decided to go to grad school for the wrong reasons. For the reason that I was really good at math, and that was the natural thing to do after being really good at math in undergrad. Turns out that it was the right decision, but for the wrong reason. I really did enjoy grad school, and it was a great place, but I decided that I didn't want to be doing pure math, which is what I had been doing. And I didn't really know what applied math was, so I explored around a lot of different fields, spent some time doing computational neuroscience, and eventually ended up in machine learning, AI, through a weird mixture of discrete math and neuroscience. Finding that intersection, it ended up being somewhere around AI, and so that was how I ended up in this area, somewhere in the middle of grad school.
So you said that you did grad school for the wrong reasons. Could you maybe explain a bit more about that?
Grad school is something that one should do if one has strong reasons for it. It shouldn't be a default. There are lots of great career paths, and academia or grad school is just one of those. These should never be seen as in any way a default or expected option. In math, often there's pressure if you're very good, and everyone expects that you're just going to go on and do more academic things, which is somewhat problematic, especially since as a society we definitely want to be encouraging people to go into lots of different careers and be really successful in those and be well prepared for that. I think the situation is better in computer science, but really there are a lot of career options, and oftentimes the default ones that people think about are not the only ones. On computer science, I think it's really good for people to consider things that aren't either academia or the tech industry, actually. Those are two often the defaults. There are a lot of great jobs, for example, in the public sector. I would love to see more computer scientists bridging the gap with policy or with implementation in those kinds of contexts, because really there are a whole lot of wonderful career paths, and we need people to be taking all of them.
Absolutely. We couldn't agree more. We're going to have some questions regarding how the academic structure works and how it can be ameliorated in the future. But for now, did you always know that you wanted to be a professor? It seems like you not really, right?
No, I considered a number of things. I considered being a professional singer. I considered certainly doing research in other things. Like I was also strongly interested in being a natural history researcher. Somehow that circled back a bit. So my group actually does work on AI applied to insects and moths. So among other things, I've come back on some of the things that I was interested in when I was much younger, which is, I feel really lucky to be able to do that. But yes, definitely, this was not the only career path. And I've also decided that when I was in grad school, I decided that I wouldn't continue along that career path if I didn't continue to enjoy it. If there will always be low periods in any career trajectory, but if there was a long period that I wasn't enjoying it, then I decided that I would think about something else.
Absolutely, yeah, absolutely. That's great advice for the listeners to the podcast.
Yeah, cool. So broadly now, what is your current research focus on?
Yeah, so my group focuses on two things. Machine learning and AI applied to tackling climate change. That's reducing the extent of climate change, what's called mitigation, and responding to the effects of climate change, which is called adaptation. And then also, to some extent, understanding climate change, which is called climate science. So it's three things: mitigation, adaptation, climate science. And then my group also works on the mathematical foundations of deep learning within AI. So I'm still a mathematician by training, and we work on understanding why AI algorithms work so well.
Okay. And has your research focus changed over time?
Oh, yes. It's changed a lot. As I mentioned, I started out in math and then ended up first in sort of the intersection of AI with neuroscience, and then on the mathematical foundations of AI. And then focusing more and more on climate change relevant applications of AI. So there's definitely been a lot of different things that I've been focusing on with different priorities at different times.
And how could you tell that, okay, now it's time for a change, or was it just something that happened with the opportunities that were available?
Yeah, so I guess first of all, I will say that I was in an extremely privileged position to be able to make various decisions about changing what I was working on, and not everyone has that flexibility for various reasons. So this is not something that I think is, I was very lucky to be able to do that. With respect to climate change, I had felt for a long time like I should be working directly on climate change. And with many of the biodiversity applications in my group, I'd also been working on biodiversity and ecology before. So that was something that was in some sense long delayed. With respect to some of the other turns that my research focus has taken, that was really me trying to discover problems that I felt were at the intersection of interesting and genuinely useful, which is an extremely difficult line to tread. And I feel very lucky to have found some problems that I think are both of those things, but it's very hit and miss.
Yeah, for sure. I mean, really to have the opportunity to focus on stuff that you find interesting and are highly applicable as well is something that I guess most people want to do, right? Yeah, for sure.
I think AI and climate change is such an interesting research area, and I'm not sure many people were working on it before. So what inspired you to work on AI and climate change in the first place?
Yeah, so I felt that I wanted to be working more directly on climate change. And AI is not the tool for tackling climate change, but it's a broadly applicable tool, and it can be used in a lot of different areas. And I, first of all, wanted to understand how AI tools could be useful within climate change. And so the first stuff that I and my collaborators were doing were very much setting out what good work has been done in this area. There's people have been working on this in lots of different perspectives for a while, but really then trying to frame the overall field of AI and climate change in such a way that it could help everyone in AI understand where high leverage opportunities are, and also understand what not to do, because oftentimes the field of AI thinks, oh, we have this powerful tool, we're just going to use it to solve everything. That doesn't work.
Mm-hmm.
If you do that, you generally solve nothing or actually make things worse. The way that you actually make a difference in any situation is by listening to the people who own the relevant problems, who understand the relevant problems, and collaborating with people in different fields, and also with end stakeholders who are actually going to be affected by it or use an algorithm.
Mm-hmm. Mm-hmm. So just following up on that, one of the papers that you contributed towards as a postdoctoral researcher, very influential paper called Tackling Climate Change with Machine Learning. It focuses on how you can reduce greenhouse gas emissions, help transform some of the technologies that we use today. We were wondering, what was the story behind that? It was a really big project that brought together a lot of AI leaders from a lot of institutions. Could you maybe tell us what the origin was?
Absolutely. So that was intended to frame where the opportunities were comprehensively across areas of climate change relevant work for AI to contribute within mitigation, so reducing greenhouse gas emissions, also adaptation, responding to the effects of climate change, and also climate science, understanding the climate. And that was really, as you mentioned, there were a lot of authors involved. That was trying to distill a lot of different complicated areas, leaving out a lot, but still trying to provide a broad overview, particularly for a machine learning audience, but also for other audiences that might be interested in understanding what this intersection really meant. So we tried to cover a lot of things. It's about 100 pages. And even with all those authors on it, we talked to many more people in many areas of specialization to gather those recommendations for what has been impactfully worked on and what can impactfully be worked on. So it's really a roadmap for people to work more, which is what we do in my lab, but also in many other groups that are working at this intersection around the world.
What would you say are the main key takeaways from the paper, and how has it affected AI development and research practices?
Yeah, so the paper has, in my view, and obviously I'm biased, catalyzed a lot of meaningful work in this space. I'm really glad to see AI for climate change applications being referred to alongside healthcare as really a key area of societal impact as regards AI. Some of the main takeaways from the paper, I guess first and foremost, we wanted to emphasize that AI is not a silver bullet. If you are interested in climate change impact and you're uncertain what tools are most impactful, AI is not something one should reach for unless it's really, really needed. But there are a lot of bottlenecks where AI can be relevant, and you can think about those as really trying to address specific problems which have already been identified in different areas of work. AI is not something that's going to come in and radically reshape the whole picture of tackling climate change. It's something that's going to make a lot of small and medium-sized impacts throughout technology and throughout society. Now, those kinds of impacts and opportunities for AI fall into a bunch of overall headings. You can think of AI playing several different roles in helping tackle climate change. One of those is in distilling large unstructured data sets into useful information for example, making policy decisions. This could be anything from pinpointing infrastructure in places where we don't understand, for example, what building footprints are, where the buildings are, and how much energy use there is from buildings, estimating that from satellite imagery, or pinpointing solar panels where we don't have a map of solar panels to model the electrical grid. Understanding what places at a very high resolution will be impacted by coastal flooding. Pinpointing, tracking deforestation in real time to help with interventions and policy decisions, or outside the realm of computer vision. So those are all applications in satellite imagery analysis, remote sensing. You could also imagine doing this, for example, with bodies of text, analyzing a large textual corpus for example, climate-relevant financial disclosures by companies and other relevant information that could be used to analyze the effectiveness of policy interventions. So in all of these cases, AI is serving some greater purpose, which is already identified, and where there's a bottleneck, and here it's an information bottleneck. The next overall theme that you can identify here is in optimizing complex systems. So AI is very good at controlling lots of knobs in a very complicated system that need to be turned simultaneously in some subtle way, and maybe a person wouldn't have patience to work this out or be able to do it in an optimal way. And so this could be thought of, for example, in optimizing industrial processes, heating and cooling systems in buildings, optimizing freight routing, interfacing between different modes of transport, things like that. The next overarching theme is in forecasting. So this could be in predicting crop yield to avert food insecurity as a result of extreme weather events that are climate induced, or in forecasting supply and demand to help balance the electrical grid down to a very high degree of resolution to prevent the need for superfluous fossil fuel driven electricity generation. And then the final theme is really in accelerating the process of modeling and scientific discovery itself. So this can take a couple of forms. It can take the form of suggesting experiments to try if there are physical experiments. That could be accelerating the design of batteries or photovoltaic cell materials, solar perovskites, for example. That is a role that AI can play not in supplanting experimentation, but in suggesting what parameters or experimental designs should be tried, given that oftentimes that is really slow, and having an automated process to speed up what needs to be tried could be very influential. It's being done in a bunch of different areas even outside of climate change, like drug discovery. And then AI can also be useful in scientific modeling discovery through speeding up complex physics-based simulations. This is not to be done on a big scale. We can't model the entire Earth with neural networks. Neural networks are nowhere near good enough for that. We have also very good physics-based models of climate, but sometimes there are pieces of them which are extremely time-intensive. And so approximating those pieces can be very useful. So taking radio transfer racing to make group works on as an example, we have these very large, intensive supercomputer-based algorithms that are run using domain knowledge in physics, and they're exact solutions to the differential equations in some sense, but that is not fast enough to be able to run at scale. If we want to get really high spatial and temporal resolution in a prediction for climate or weather, we would need to have a fast approximation. So AI can provide sort of quick and dirty approximations for certain of these otherwise very time and compute intensive processes.
Mm-hmm. So from what I understand, it seems to me that you're applying solutions, AI-driven solutions, to problems that we have identified in the past and we know that exist.
Exactly.
So some of the things that you mentioned and I've read about being applied are, for example, DeepMind using their algorithms in order to improve their data center energy usage, or Facebook using machine learning to sort of provide better load balancing for their servers. And I've encountered researchers at McGill who are using ML techniques in order to invent new batteries. So, all great examples of what's being done within this field.
Yeah, you're really leading a vision and building a community around tackling climate change with AI. I was wondering, what are your thoughts around how the governance structure and the ecosystem for tackling climate change with AI would look like, and what part can a researcher play in that?
Sure. So coming out of the big paper on tackling climate change with machine learning, we founded an organization called Climate Change AI, which is a global nonprofit which aims to facilitate the overall space and catalyze impactful work at the intersection of AI and climate change. So many of the things we do are involved in helping shape the governance structures that are needed in order to facilitate work in this space. There are a lot of things that are needed here. Some of what we do in the space is to really connect different communities. So that's different research communities, but also communities of stakeholders who will be deploying systems, in addition to those who are developing them, because one really needs to consider the end use of any technology right from the start. If you develop something with publication in mind, then it's not probably going to be useful to the actual people who are going to be using it. So this kind of bridging gaps is maybe not a governance structure from the perspective of governments and policymakers, but it's something that is more actionable in terms of governance within the research community at large. And similarly, incentive structures really enabling people to focus on genuinely meaningful work at this intersection. So we're also developing publication venues and venues for researchers to develop meaningful work and present that in the broader scientific community. We also work on funding structures. We just finished our first round of proposals for our innovation grants program, and the first round of winners will be announced soon for that. But more broadly, there is a lot that needs to be done from the policy side, and some of that is more broad than just AI. A lot of the governance structures that are needed here are interventions more broadly in technology. So, for example, considering how a new technology that is being developed can be shaped with climate change in mind. So, for example, self-driving cars are probably going to make climate change worse. because they are, if we're focusing on personal cars, then that will lead people to drive more because driving will be easier. And so even if each mile driven is a little bit more efficient, then we can assume that there will be more overall consumption of fuel for driving. However, if autonomous vehicle technology is steered towards shared transportation and freight, for example, there's the opportunity to make it actually be a climate benefit. So that kind of thing, really realizing that AI as a field can be shaped in different ways is really important. Now, there are a lot of sort of more technical points, like data sharing standards and structures for international cooperation, deployment and capacity building initiatives, such as secondment programs in industry. And I'd be happy to go into details on any of that. We do provide recommendations to policymakers as well on this. So that's definitely something that is very needed, and it's needed to think about how climate relevant considerations can be incorporated, for example, into national AI strategies. I am part of the committee within the Global Partnership on AI on biodiversity and climate change. And Climate Change AI as an organization also works on shaping recommendations in this space.
Okay. I mean, that is, yeah, you talked about various like applications of like how governance can affect shaping AI. So I was actually curious to start off with, in terms of academia, you mentioned that you are developing or proposing new funding structures that could incentivize researchers to work for more, meaningful applications such as climate change. Was that something you were talking about?
Yeah. So we had the first round of our grants program, which was about $2 million on specifically applications at this intersection, which will be distributed to the winning proposals that were submitted for our grants program. We hope to have future iterations of it and to enlarge this funding structure. But also we work with other organizations to help shape other funding possibilities. So for example, the Tackling Climate Change with Machine Learning paper also influenced the development of other funding programs, such as, for example, the Differentiate program in the US run by the Department of Energy, a program by Vinnova, the Swedish grant-making organization, and others. So we're really working to try to create an overall funding environment that is more conducive towards this kind of work.
Okay. And then the other big aspect of, from the academic standpoint, is stakeholder research, right? So what does that look like from a researcher standpoint? Let's say they're working on a specific application. What does that look like from an academic standpoint?
I'm going to talk more to the AI side of things because, given my understanding of the audience of this podcast, it is essential to listen. That is really the key point about collaboration. Listen and don't go in with assumptions, because you can be the expert on the computer science and AI, and they may not understand algorithms at all, but they do understand what the problem is, and there are always nuances at every level. Think about how something is going to be used, first of all, from the perspective of, is the problem that we are solving actually useful from a climate perspective? And if so, exactly how? How is it going to be used? What is necessary to build in to make sure that it is actually useful? Right? Because it's very easy to think sort of in keyword terms. I want to work on fires because, I see that fires are a climate relevant problem. Well, what exactly are you going to do? I mean, you could take a data set and put out some predictions, but is that actually useful for relevant stakeholders? Talk with people, talk with fire researchers. There are always researchers in a relevant area. Learn from them, do reading. There are lots of impactful problems. But to find them, you need to learn about the specific area in question and work with people who understand the whole pipeline. Also think about what problems you know about and how your bias shapes those things. Like, a lot of people are working on forest fires, which are extremely important to work on, by the way. But by comparison, there's very little funding going towards, say, locust infestations in East Africa, because there are funding streams which are very North America focused. And when Silicon Valley has forest fires every season, then people in Silicon Valley get worried about it. But there's maybe less money in the Horn of Africa to spend on startups that are applying AI to forecast locusts. That's happening too, and it's a really great application. So think about what your focus areas are and what you're aware of, maybe shaping what you immediately think about. So really learning at the broad level as well. But then in terms of any particular project, it's really necessary to work throughout in close collaboration with people who understand the problem, because also you're leaving out a lot of information if you don't understand the constraints and the meaning behind what you're doing. Very rarely in the real world do you just get given a data set and a set of metrics, and your success and your impact depend upon getting the maximal accuracy on that data set. This is almost never the case. We're training our researchers to do the wrong thing. In certain cases, there may be a reason why an extra 1% improvement on a data set is useful. But in many situations, just like creating the data set is a bottleneck. Making it in a form that is amenable to machine learning, and then getting any kind of decent performance is often really, really hard. So, or alternatively, using a really simple algorithm that's not extremely fancy is completely sufficient. So often there is room for innovation in this space, but don't go in assuming that the hard part is going to be some major algorithmic innovation. There are a lot of opportunities for huge algorithmic innovations, but oftentimes another hard part is just understanding the problem and shaping it in such a way that it is amenable to intervention by machine learning. Get very used to spending a lot of time working with poorly formatted data as well. That is always a huge amount of time, but it's worthwhile also because once you've done it, then other people don't have to do it.
Absolutely.
Sounds like that's a very different process from like pure academic research. So I think in academia, people use the number of publications as well as the number of citations as a metric for the impact of one's work. So when it comes to a more applied field like this, when you're trying to solve an actual problem and working with people towards that problem, how do you quantify the impact of your work in this case?
Yeah, so it's not that one doesn't get publications and citations in these areas. And oftentimes there are actually really interesting methodological challenges associated with understanding deeply a domain-specific problem. So as an example, one of my group's recent publications in iClear, so one of the machine learning conferences, was purely driven by a specific domain problem in electrical power optimization, what's called AC optimal power flow. And the reason why this became an extremely broadly useful algorithm is because we really thought about what was necessary here. In this case, we had a big non-convex optimization problem, and it was needed to solve it approximately because what was being done was that it was being simplified so much that it was essentially unrecognizable, and the solutions were very, very far from optimal. But the reason why it was being simplified because solving non-convex optimization problems exactly is very hard. And this problem, which is to do with understanding power on the electrical grid, has to be solved every few minutes, especially if you have more renewable power. So in order to fix this bottleneck, one needs to solve this fast, but there's huge inefficiencies in how it's being solved, and that's leading to a lot of overproduction of electricity, huge waste. We realized that we needed an algorithm that could approximately solve non-convex optimization problems. But the key constraint was that there were hard constraints in the optimization problem. And if you broke feasibility, then you would make the power go out. And so understanding that one needed to solve a non-convex optimization problem fast with hard constraints led to an algorithm that was actually generalizable across non-convex optimization problems and is very broadly useful. So oftentimes there will be these kinds of situations where one has a domain-specific problem that leads to some breakthrough methodological innovation. There's so many of these cases: interpretable machine learning, hybrid physical models, uncertainty quantification, transfer learning. These are all cutting-edge areas of research in machine learning, but they're also exceedingly relevant for all these for many climate change relevant domains. And those are the perfect test cases for really delving into a meaningful algorithm that can not just make a huge impact, but also push the boundaries methodologically.
Absolutely. Yeah, I think you offered some great advice points. I was wondering, and this might be a bit pessimistic on my side, but obviously you mentioned that there are a lot of ways that governments can incentivize, the type of research that we want to see. There's a lot of ways that companies can change their practices or change their application so that it's more beneficial. But for me, it seems as though the underlying assumption behind those is that people do care and people actually understand what the challenges are. When I look at the sort of ecosystem as it stands now, it seems as though the media does not focus on the issues of, AI applications. It's more so just like, oh, the robots are coming, or, it's the end of us all. How do we fix like the discourse that surrounds AI so that people understand that it's not the end of everything, but also there's some serious issues that we need to address?
Yeah, people in the media and members of the public will often focus on the wrong things when it comes to concerns about AI. I'm terrified by AI, but I'm not terrified that we're going to have killer robots. I'm terrified that we're going to have decisions made in areas where AI should not be making decisions, and AI perpetuating or exacerbating biases and inequities and making them seem objective, or just outright being used for bad things to accelerate things that I do not think should be done, period. Now, I don't have a simple fix for that. I do think that I think that one thing that's really important to remember is that the societal implications of one's work are not somebody else's responsibility. You are shaping how your work is done, and if you aren't doing it actively, then you're doing it implicitly. You can't back out of how AI is relevant in society. Often we think of AI for good as a separate area. No, AI for good is hopefully all of AI, but it's certainly a consideration for any kind of AI. Let's take climate change, right? AI can not just make climate change better, it can make it worse. Lots of AI is being used, for example, in accelerating oil and gas discovery. The oil and gas industry is expected to make $500 billion extra in profit by 2025, thanks to AI and analytics. A lot of that is making climate change definitively worse.
Absolutely.
Similarly, recommender systems, AI being used in advertising, is making climate change worse by increasing consumption around the world. One's choices as an AI engineer or researcher are implicitly changing society in very big ways. And understanding that is a step towards the field overall being more explicit and transparent about what change through AI actually means. So communication is one part of it, but another part is really consciousness of what AI decisions actually mean. But at the low level, talk to people, understand what it means to be communicating one's work to different audiences, to a scientific audience outside of AI, to a non-scientific audience, and then think about the implications of your work and how you can shape that, because it's really exciting. We get to choose to some significant degree how our work is impacting society, even if we're not working explicitly on like deforestation or something. You don't have to do that to be having a significant impact and to be shaping that impact. There are opportunities at every level to really positively benefit the world, and change one's work, steer one's work in ways that are meaningful.
Absolutely, yeah. So because AI is applicable towards so many different sectors and different fields, I was wondering how much focus you yourself give towards understanding, let's say, physics, chemistry.
Sure. Yeah. It depends very much on the project. I think that it's important, if one's working in a cross-disciplinary collaboration, to have some measure of understanding of other field, but also trust in one's partners to provide deeper understanding, because one's never going to become an expert in a few months on a field that one hasn't interacted with before. But at the same time, some degree of literacy is important for breaking language barriers between fields and just generally understanding what is going on. So I think it's a mixture.
Okay. Yeah, that makes complete sense. Yeah.
So let's take a look at your work in deep learning theory. So we know that you've also done some really great research in deep learning theory, like understanding neural networks. So one thing that people have been talking about is there hasn't been much algorithmic innovation in the field of deep learning. It's just that nowadays we have the compute resources as well as the data set to really scale up these models. So nowadays, people talk a lot about scaling laws and Rich Sutton's bitter lesson. And we were wondering from like a theoretical perspective, are we making a lot of progress in understanding neural networks? And do you think we're making a lot of algorithmic innovation for neural networks? And is there much more space to improve in terms of the algorithmic innovation as well?
Yeah, I think that there is a lot of algorithmic innovation that is happening, even though it's sort of concealed by a lot of innovation that isn't truly innovative. There's a lot of just stuff happening in machine learning as a space, and it's easy to think that the field is moving very fast, and it's moving. I don't think it's moving as fast as it seems, but it is definitely moving and advancing. We aren't building the theoretical foundations at a similar rate to how we're building essentially heuristics. That is coming. We're sort of at the stage of building airplanes that work pretty well, but not really understanding how fluid dynamics keeps them up. So that is an issue. You ideally would want to have a rigorous understanding of why your systems are working and when they may fail. And also, I rather expect that deeper theoretical understanding will enable us to open up completely new pathways of innovation that haven't previously been possible because we didn't understand how things were working. So I think there is a lot of there are many innovations happening on both the methodological and the theoretical level, but I'm very excited for there to be more solid foundations, which I think will drive increased and maybe more groundbreaking innovation moving forward.
Okay.
Do you think it's possible to build like a much better foundation for understanding neural networks? Because I know deep learning nowadays has a lot of like explainability problems, and it seems like most of the theory work is done on really like toy-ish models, like maybe neural networks with like 2 layers. So do you think it is possible for us to really understand and for us to really model theoretically the behavior of like large neural networks scaled up on these like huge data sets?
So there are different notions of understand, and this is talked about a lot in the neuroscience world. I don't think we're going to have an understanding of deep neural networks in the sense that we like know what every neuron does. That's not the way that deep neural networks work, and that would not be a kind of understanding that I think we should strive for, because it's ultimately hopeless. I do think we can understand more general principles that do generalize beyond the simple test cases, which you're completely right. A lot of the theoretical work has been focused on simple test cases, but I would say that part of that is simply because we didn't even have the theory for the simple test cases. We're trying to get there, but it's amazing. We really didn't have the theoretical foundations, even in simple situations. I do think it is possible to have some theoretical framework in more complicated settings. It's just one will have to settle for conceptual understanding and theoretical principles that are maybe at a larger level than full interpretability, because I don't think interpretability is something that's going to come out of theoretical understanding.
Okay. I have a question. So let's say, someone is looking to get into AI. Would you suggest having a good understanding of sort of linear algebra, intermediary calculus, or is it okay if a high schooler is like, okay, I'm going to import PyTorch, import sklearn, and just, start looking at stuff? Like, do you see an issue with perhaps people not understanding the like underlying mathematical fundamentals and starting?
I see some issue with that. I don't think it's a problem if you start out with a different set of practices. Learn things however you want. I do think it's necessary to have some kind of an understanding of those principles by later on, because otherwise you really are sort of building on sand a bit. I've learned many things where I didn't learn the foundations until much later, but I think not knowing those foundations, if you are going to make that a serious part of your career, is a problem, because that can lead to a lot of pitfalls, methodological pitfalls, if nothing else, right?
Yeah, that makes sense. That makes sense. Yeah.
What are some examples of the pitfalls, if you could give any?
Yeah. So there are many situations in which relatively simple math is going on, but is not understood at the engineering level. For example, I had one paper which pointed out that the initialization scheme, which was used by default in PyTorch and Keras and a bunch of deep learning packages, was actually wrong, like provably wrong.
So just to clarify, the initialization of the weights of the
the initialization of the weights of the neural network. Now, there were reasons why people had done this as a heuristic, but there was a gap between however it had been implemented and the original papers that had set up these initialization schemes.
Mm-hmm.
And because the engineers probably hadn't understood the motivation, they had set something up in a way that actually led to deeper networks failing to train.
Oh, okay. Okay. Yeah. No, that's a great example. Yeah. So what was the issue with the initialization?
Well, for one thing, they were using an initialization scheme that was designed with one activation function in mind and using it for every activation function.
Okay.
And another issue was that they were truncating the normal distribution and not making it clear that they were doing so, which actually broke the ability to train for deeper networks. Now, there are reasons for doing various things, but it was done in a very non-transparent way that made one think that they didn't really understand the implications of the decisions that they were making.
Mm-hmm. Mm-hmm. Okay, that's a great example, I think.
Okay. So we know you've done some research on the advantage of depth in neural networks. So yeah, we were wondering about that. Are deeper networks more expressive, and are they harder to train? Do you want to talk about that?
So it's a really interesting topic. What we found in a number of different papers is that there are various ways of characterizing the power of a neural network. And one is simply in terms of what functions the network is capable of expressing. Like if an oracle gave you a magic network, could it express this function?
Mm-hmm.
And what we found in a number of situations is that deeper networks are better at this. And other authors have found similarly that if you're trying to represent more functions, not more functions, but in some sense greater complexity functions for some notions of complexity, deeper networks are better at doing this.
Mm-hmm.
But, and it's a big issue, they don't in practice necessarily. So if your oracle gave you the right network, that network would exist more if you had more readily and with fewer parameters if you had a deeper network. But in terms of the likelihood of you're actually finding it yourself through a learning algorithm, there isn't as much of a difference. It's not clear that deeper networks are actually better from an expected complexity perspective. They're better from a maximum complexity perspective. And some of the really useful networks that you might want to learn are actually provably hard to find. Some work that I've done, and also some work that other people have done. For example, the XOR function. If you are trying to learn the XOR function, it's provably hard. Like you won't find it, even though there's a very succinct representation of it in a very small neural network that leverages depth, but it is very hard to find that network. Now, more broadly, you can imagine there being lots of situations where there's a difference between what you theoretically could express if you were given the right network and what you can actually find. And what this gets at is, more broadly, how we design neural networks is important, not just because they give us the ability to express complicated functions, but because they give us inductive biases towards functions. And there's a blind spot in deep learning often, which is that we don't necessarily know what the inductive biases are, and we're implicitly using them without actually ever having described them. Oftentimes, this takes the form of somebody saying, well, this algorithm works, and it's able to express all possible functions. That means it's unbiased. No, because it works, it is biased. It's just biased towards the things that you want. And so we need to understand this more broadly, because we're building in biases to systems and sometimes forgetting that we've done that. And if we don't understand what kinds of functions are coming out, either at an abstract level or very concretely, what kinds of results a deep learning algorithm is giving us in a real world task, we are in some sense flying blind.
Okay. I think that's very interesting because, a lot of people, I guess the mathematical background says that you can actually represent any like complex function with two like layers, right? But often the change that what we're seeing in industry and academic practices is that we're getting deeper and deeper networks which leverage those inductive biases.
It's a mixture of leveraging inductive biases, and as I mentioned, like the deeper networks are able to represent functions often with fewer parameters, and then there are also different inductive biases for deeper networks and shallower networks, and those are poorly understood. So in certain cases, yes, we're seeing that there are in practice better, more useful to us inductive biases, but I think the jury's out on exactly how to quantify that in a lot of cases.
Okay, gotcha.
How do you define a complex function, as you mentioned?
Yeah, so a complicated function can be complicated in all kinds of ways. There has been work from my group on, for example, the volume distortion, where we have recent work on distorting lengths and volumes. You throw in something of one length or volume, see how it can change as you put it through the neural network. We've also looked at number of linear regions. So if you have a ReLU network, it's actually piecewise linear, so you can divide it into regions of the input space where it's just computing a linear function. And how many different linear pieces you have, that gives you the ability to get a more complicated function. People also looked at curvature, and various topological invariants if you want to get really mathematical. And then in one paper, we just looked at degree of polynomials, where if you're trying to approximate a polynomial, you can just think of the degree of that polynomial as a measure of complexity.
Okay. Yeah, those make sense. Well, you mentioned that you worked with, or you established an institution called Climate Change AI. We also know that you worked on an institution called Sustainability in the Digital Age. Just to provide some context for our listeners, Climate Change AI is a global initiative to catalyze impactful work at the intersection of climate change and machine learning. And Sustainability in the Digital Age is leveraging the digital age to drive informative system changes for a climate-safe, sustainable, and equitable world. What we were curious is how is it like managing these initiatives and institutions?
It's a great question. I view this as all part of different ways of making change happen. So as a researcher, there are certain levers that I have and that my group and students have for making change occur via innovations methodologically or combining new combinations of methods and applications. And from the perspective of, say, Climate Change AI, we have the ability to run events bringing thousands of people together at this intersection, or provide funding, or shape policy. All of these are necessary in some sense in order to foster the right kind of change, and they all have to be done that's why I have different hats on, but they really all work together.
Okay. And we know that you were someone who organized an event at the Climate Change Conference. You've worked with the UN in the past. What has your experience been like working with policymakers, legislators?
Yeah, policymakers, obviously, like any other group of people apart from computer scientists, they will speak a different language and have different priorities. I think that fundamentally, I think there should just be more discourse between academics and policymakers. There are huge gaps in understanding about what is important between the academic community and the policy community, going both ways. Oftentimes, academics don't realize what is necessary to think about from a policy perspective. And oftentimes, policymakers are concentrated on some small things that they know about an area, or like anecdotes, essentially, without really having a deeper understanding of how these fit into the overall picture. So more communication is really fundamentally important. But fundamentally, policymakers are really interested in AI work, and I've found that people are surprisingly literate. Like maybe I didn't have very, very high expectations of people outside AI, but there is a lot of understanding, there's a lot of interest, and there's a lot of dialogue people looking to have dialogue. So interacting with that and being a part of the global conversation on how to set up systems is really, really important.
It does seem, though, that you are an advocate of students who have technical backgrounds going in to become policymakers and legislators. Do you want to give like a quick pitch on why it's important? And
well, I guess, first of all, there are a lot of ways to be involved with policy. You don't have to become like a politician. You don't have to become a legislator. There are I would like to see more people in computer science go into the civil service, essentially, or go into facilitating government agencies, things like that. There are all kinds of ways to do that in ways that are very, very technical. Everything from like actually working on research to interfacing between research and deployment, or working on the funding processes and the capacity building processes for policy structures and public sector structures. A lot of them are really exciting. Like, for example, there is an initiative called AI for Cities, which is focused on how this is EU focused, that is about thinking how AI can be integrated meaningfully into cities at different levels, for example, through procurement programs, in order to drive sustainability impact. And this is a really great mixture of sort of policy on the ground and technical expertise, and I want to see more of these things and more interfacing between different people in these kinds of institutions. That said, I think there's also a significant role for practitioners who are sort of solely in the AI domain or in other technical domains to just interface through initiatives like workshops and institutions like the Global Partnership on AI that really try to provide dialogue between different kinds of stakeholders. And ultimately, one needs to interface with stakeholders in order to have impact for one's own work, in whatever one's own work is. So really being cognizant of that kind of dialogue, whatever part of the dialogue you want to be, whatever place in the dialogue you want to take.
Absolutely, absolutely, and I think it's important to emphasize that if we use like the space race as an example, in the U.S. they recruited the best engineers, the best scientists, the best technologies to solve the problem, and we could do the same with climate change. I think it's very important for us to realize that privatization helps with scalability and commercialization, but public institutions really can take the risk and recruit the talent in order to solve some of the biggest problems that we're facing. Yeah.
And to be clear, I completely agree with what you said. To be clear, I'm not against people going on and doing this in the private sector. It's just I think that gets talked about a lot more. I think that's fundamentally important. I'm really glad to see the number of entrepreneurs, startups coming out of AI. I'm really excited for those in the climate change space. So many different areas, everything from ag tech to energy technologies, and so many different settings. Mm-hmm. I just think sometimes we forget about the public sector.
Mm-hmm. Absolutely, yeah, I completely agree.
Yeah, I guess speaking of the implications of one's work and in terms of ethics, do you think the current undergraduate or postgraduate curriculum is doing a good job in helping the students considering the ethics of their work? And what do you think that can be done better?
I can't speak to like McGill specifically, but I think overall the field does a very poor job of this. As an example of the kind of failure mode that one just sees everywhere in AI, Amazon decided that it was going to introduce an AI algorithm to automate the hiring process in certain situations. And they said, oh, well, we obviously don't want to include gender as a factor in the machine learning algorithm's decisions. So we're going to take out gender from the data set. And then they created a machine learning algorithm and it hired only men. And obviously the machine learning algorithm had been given a data set which was extremely gender biased. And it worked out 100 different proxies for gender, from which it was able to work out what people's gender was to some extent, estimate that, and perpetuate and make objective seeming the biases which have been introduced by the almost certainly male engineers who had made this. So this is a situation where the decisions that are being made on an engineering level and the decisions that are being made on a management level in AI are fundamentally misguided. In my opinion, we shouldn't have that kind of algorithm at all because there's no way to actually deal with this. But certainly this kind of thing is not being taught to people sufficiently. It's not being taught to people at the level of how can you shape your algorithms to make them have the desired effect and be as beneficial as possible for society. It's also not being taught to people in terms of you get to choose the problems that you work on or choose not to work on certain problems at all. Certain things shouldn't have AI.
Mm-hmm. Mm-hmm. Absolutely.
And oftentimes we're just giving people hammers and saying, go forth and hammer. And nobody's being taught where you should use a hammer. Mm-hmm. They're good hammers, to be clear, but it's like only in certain circumstances should you be doing this.
Absolutely. So what is something like actionable, let's say in an introductory machine learning course, that can be done to tackle this? Like, for example, you mentioned like for me at least, it seems obvious that feature selection should be done in a method that if you remove something, you want to ensure that other features that are correlated should be as well. How do you how do you teach for students to consider the ethical implications of this?
Listen to the fairness and ethics researchers. There are a lot of them. Watch Coded Bias. Listen to Joy Laborlamwini. Listen to Timmy Gebru's talks. People are thinking about this, but it's complex. Teach the problems, even if we don't have solutions to them. One doesn't have to say, this is how you fix it. Because right now, we don't have ways of fixing many of these things.
Mm-hmm.
And teach problem scoping, right? Like, oftentimes our curricula are focused on answers, more, how do you solve this? How do you solve this? Rather than how do you pick questions and how do you scope and change those questions?
Mm-hmm.
That's much more important than how do you solve them. Because if you're solving the wrong question or solving it in the wrong way, that can do active harm.
Absolutely. Yeah, that's a fantastic response. Yeah, for sure. So our last segment is dedicated towards some advice for students. We noticed that on your website you shared a piece providing advice for PhD students. What prompted you to share that, and could you share some of what those tips were?
Sure. So I wrote that piece fresh out of my own PhD, thinking what it would have been useful for me to have known, or that I saw other people finding useful. And it's done by many people. You'll find many of these words of sage advice from people who have just graduated from their PhDs. But for me, some of the takeaways are thinking about mentorship, making sure that one trying to develop mentorship in multiple different ways, thinking about the acquiring support not just for research, but for professional development, about things one's interested in, about hobbies, about just life, making sure that one is providing oneself with support structures in lots of different ways from lots of different people. That is something that I touched on. I touched on science communication, really thinking about having as many opportunities as possible for communicating one's work to people in the field, people outside the field, members of the general public, traveling as much as possible. I understand present circumstances make that difficult, but really interfacing with different communities is really the point of travel, and finding collaborators outside one's institution, finding just people to talk to. Most of my collaborators came out of friends I made at conferences. That's the kind of, or within the same institution, that's the kind of conversation one should be having without an agenda. Same thing with mentors. One should talk with mentors without an agenda to learn from more people and to strengthen relationships that may end up being foundational in sort of concrete ways. I also talked about scoping problems there, but maybe some advice that I can add, or some of the things that I talked about maybe a slightly different way. Grad school is hard. Everyone I know who has been a grad student, myself included, has gone through periods of depression, has gone through periods that seemed really, really hard and were really, really hard. And there are a lot of reasons why that's the case. And basically, none of them are your fault. There are sometimes ways that, if things seem really bad, there are sometimes things that can be done to make them concretely better. So it's not to say don't try, but it is not your fault if something feels really hard. The systems are at fault. Sometimes other people are at fault, and sometimes just circumstances. I really enjoyed grad school on the whole, but it was also really hard. And remembering that it's not you is sometimes useful.
Absolutely.
Yeah, on that note, I would also very much remind people to take time for self-care and healing at all levels. I actually write down things that I need to remember to do to stay okay, things like running and sleeping and cooking and reading, and setting aside specific time for those things and making making them automatic. Like, I will do this every day regardless. That's the kind of thing that I think is really, really important. And also remembering that not just setting aside time at the small scale, but also at the larger scale, making sure I can go for a long time without a holiday, but I'm not okay by the end of that time. So that's really important too. Not just setting time aside on a short-term basis, but also on a longer-term basis for self-care.
Absolutely. I think, even on an undergraduate level, we sort of come into university thinking, all right, we're ready for the grind. Often people don't even take breaks after like finishing their high school curriculums. We sort of go straight into it, and we in general experience these phases where things are hard, like really hard. And I think it's very important that people focus on self-care, people focus on their hobbies. So I was wondering, for you, do you think that focusing on those things, reading, hiking, traveling, made you a better researcher?
Absolutely. So in the sort of, in the very immediate and rational sense, like, I work on AI applied to entomology now, to insects. That was originally a hobby. That said, I think most of the ways in which they have made my career better is by simply making me more okay. I can't work if I'm not okay. So even if you're just optimizing for your career, not optimizing for your happiness at all, you will do better work if you are okay.
Absolutely.
And different things are necessary to help you if you're a different person. For me, like, I need to sing opera periodically, but other people may have other things that they need to heal.
Absolutely. Yeah.
Yeah, those are some really good tips.
Yeah.
One thing you wrote is build a foundation for your dreams. Don't go for the moonshots. Don't go for the moonshots directly. Instead, build a foundation and work towards that step by step. I think that's really interesting. I think especially for young students, like, we tend to get really excited about things and then tend to want to work on really big problems. So how would you advise students, like, how to balance this, like, excitement for big problems versus this perseverance in building smaller steps towards that problem?
Yeah, you don't get to the moon by jumping progressively higher. You get to the moon by working out what the intermediate steps are. You should still, like, think about moonshots, but really, like, try to define anything that you're working on that is really a big dream very clearly, and make it about smaller things first. You remember what your goals are and what you care about. Those will be really important in motivating you, and hopefully you'll get there. But oftentimes, especially, if you're working with you can end up working with a mentor who gets really excited about them too and wants to give you something that's very pie in the sky to work on. That's risky. Make sure that what you're working on is building a foundation, and also make sure that it's not motivated by somebody else's idea of what they want to achieve. Oftentimes, again, you can have a mentor who gets very excited about something but doesn't really think. They have maybe lots of students, and they have the high variance approach. Give everybody moonshots. Maybe one of them will work out. Great for the professor.
The venture capital approach.
Yeah, exactly. That's not a way to actually work with students. Now, only some professors do that. I'm not trying to say that this is necessarily what's happening, but for students, maybe unlike for VCs, you really need to think about doing everything in a way that de-risks and that is going to get you to places that you want without jumping for the moon. It's also the way that startups should work too.
Yes,
to some extent.
Yeah, absolutely. Okay, so I think we'll end it there. I can't thank you enough for taking the time. I thought we had a fantastic conversation, and especially with regards to what students should be looking at, what the governance structure is, all the amazing accomplishments that you've had so far, and we can't wait to put this out.
Yeah.
Thank you so much for having me today.